Welcome back. Today, I want to look at an introduction to functions. Now, so first I define what a function is, and I've said that a function f, so I'm using small letters like f, g, h, and so on to denote functions. So a function f from an empty set A to another an empty set B will be a rule that assigns to each element of A exactly one element in B. Now, so you know what a set is. A set is just a collection of objects. For example, you can say that set A has the elements A, B, C. So it's a collection of these elements. So what I'm saying A, and I have another set B that has elements E, F, G. Then a function would be a rule that assigns to every element of this set A exactly one element in set B. That's what we call a function. And as I've said, I'm using small letters F, G, H, and so on to denote functions. And I'm using capital letters to denote sets. For instance, set A, set B, and so on. Now, what is very important about the definition is that every element in A must be assigned to an element in B, just one element. And if that happens, then F will be said to be a function. Now, so if we are assigning from A to B, then the elements in set A, we shall refer to them as objects. Elements in A shall be referred to as objects. For instance, A, B, C here will be objects, and the elements in B, we shall refer to them as images. We shall refer to them as images. Now, so what that therefore means that every object must have exactly one image. One image must have one image. Every object must have one image. Now, that's what this definition says. That a function f from an empty set A to B is a rule that assigns to each element of A exactly one element of B. So that is what I can explain about this definition. And it's very important for us to know what the definition means. And that's what I've written here. I've written here and I've said that, in other words, just a minute. I've written here and said that, in other words, a function is a special type of relationship where each input, which I've referred to as object there, which each input gives a single output. So the output for the image. So each input must give a single output. So we should not have cases where one input gives two outputs. If one input gives two outputs, then that is not a function. And where we have other objects also not assigned to images, then again that will not be a function. Now, so the set from which we are assigning the set that has the objects. For instance, I have A, and we are assigning to elements of A, we are assigning B, elements in B. Then this, if F is assigning elements of A to elements of B, then this A shall be called the domain of the function, the domain. So the domain is the set from which you know what a function is by definition. I'm just saying that a function is just a rule that assigns to every element of A single element. To each element of A rule that assigns to each element of A single element. Now, so let me show you by use of a diagram what that is. So I've used this arrow diagram to help you understand what a function is. And look what this is set X. Set X has the elements A, B, C, D. And then we have set Y, which has elements E, F, G. So I've called this X the domain. That's what I've told you before. This is the domain, the set from which you're mapping, and this is the codomain. So we are assigning every element. What you realize here that every object or every element in X has been assigned an element in Y. So this is our function F. So F is assigning A has been assigned E. A has been assigned E. B has been assigned F. C has been assigned F. D has been assigned G. So what we notice that every element in X has been assigned a single element in Y. And therefore, F here qualifies to the function. Our F qualifies to the function. Let's look at G here. We have set A with these elements, and then we have set B with these elements. Let's see whether G is a function. The first element that I see in A is 1, and 1 has been assigned 2 images, 7 and 5. There's no need of looking at other elements. This one is enough to disqualify G from being a function. So G here is not a function because this object has 2 images. We say that for it to be a function, every object must have 1 image. But you notice that 1 has 2 images, 7 and 5. What about the rest of the other objects? 2 has 1 image, that is 8. 3 has 1 image, that is 10. 4 has 1 image, that is 9. 6 has 1 image, and that is 9. But this first one disqualifies G from being a function. So G is not a function. I'm just helping you to understand the notion of function, what a function is. So these diagrams were meant to just help you understand what a function is. So what is here is this just explanation of what I've already explained. I've said figure 1.1 shows that every element of X has been assigned to a single element, and this is very important, single element. And the other thing that is very important here is that every element of X must be assigned a single element of Y. So therefore, F, which assigns elements of X to elements of Y, is a function. And this is how we write it. So we say that F is a function assigning elements of X to elements of Y. Or F is a mapping. I can use the word mapping, but I don't want to use the word mapping here because I've not introduced it. So let's just this function. F is a function which assigns elements of X to elements of Y. And so this is how we write it. We can also write it like this. F is a function that assigns elements of X. So supposing X is in this set X and Y is in this set Y, then we can write it this. We say that F is a function which assigns element X is assigned to Y. Element X here is assigned to Y. That means the image of X is Y. On the other hand, I've said figure 1.1b, this figure here, shows that G, which assigns elements of A to those of B, is not a function. And we said the reason is that because element 1 has been assigned 2 images, 5 and 7. So that means that G is not a function. So you need to know if somebody gives you a diagram or an equation to tell whether something is a function or not, you should be able to use that knowledge. Check to see whether all the elements in the domain have been assigned to images, and if every object has 1 image, just check and see. So let's look at this other example. The example says, let F and G be 2 rules from set X, which has elements -1, 0, 1, and 2, to set Y, which has elements -1, 0, 1, 2, and 6. Rule F is defined as F assigns elements of X to those of Y, such that F of X equals to X plus 1. While rule G is defined as G assigns elements of X to those of Y if Y is given by X squared plus X. So the question is, are these rules functions? So before we answer that question, it's important for us to know what the question wants us to do. Let me just first of all explain to you what those rules mean, what the rules here mean. Just a minute, where was it? Let me just go back to it. Yeah, here it is. Okay. Now, so let me define what this rule means. We've been told that F assigns elements of X to those of Y, and is given by, this is what I'm looking at. F of X is X plus 1. What this means is that if the object is X, the image will be X plus 1. That's what it really means. If the object is X, the image will be X plus 1. That means if the object is 2, for instance, if the object is 2, so what you're seeing here is that where X was, I've replaced 2. So that happens also on the right-hand side. Where X is, I replace 2. That means that if the object is 2, the image will be 3. If I'm using this definition. That's what I want to use. So I want to see whether F is a function. So I just want to see, considering these objects, what will be the images here? What will be the images of this object? Let's just go one by one. One by one. So the definition is that when object is X, if the object is X, the image will be X plus 1. So what about if the object is -1? So if the object is -1, the image will be -1 plus 1, which is 0. So that means that -1 will have the image of 0. What about if the object is 0? So if the object is 0, the image, using this definition, the image will be 0 plus 1. So while there is X, I'm just writing 0. This will be 1. That means again that the object of 0 has an image of 1. What about, so just check, first of all, before we go far, we check if the image, this image 0, if it's here. Yes, it's there. The image 1 here, is it here? Yes, it's in Y. It's in Y. Then we come to object 1. So if the object is 1, What will be the image? Where there is x, I write 1, n plus 1, that will give us 2. That means that when the object is 1, the image will be 2. So 1 is assigned to 2. Is 2 there? Yes, it is. 2 is in y. Then lastly, we look at this element 2. So if the object is 2, what would be the image? So if the object is 2, the image by definition would be 2 plus 1, which is 3. That means 2 is assigned to 3. And be written the set of ways. This is the other way we can write that f assigns element -1 to 0, assigns element 0 to 1. Not 3 is not in, but 3 is not in y. What we have in y is 6. So that means that this f is not a function because this 2 will not be assigned any element in y. Will not be assigned any element in y because we see elements in y are this, but there's no 3. There's no 3 there. That means 2 will remain unassigned, and therefore f is not a function. Let's see how the diagram would look like. The diagram will be, and the diagram I'm just getting from here, that -1 is assigned to 0. You can see that -1 is assigned to 0. That 0 is assigned to 1. 0 is assigned to 1. And that 1 is assigned to 2. But 2 is not assigned any element. 2 is not assigned any element. So you realize that there is this object that has not been assigned to any element. So by definition, f is not a function because by definition we say that every element in x must be assigned an element, a single element in 1. That's what the definition says. Let's go back to the definition of C, if that is what it is. The definition says that a function f from an empty set y from an empty set B is a rule that assigns to each element of A, exactly one element in B. So that definition that disqualifies our f here from being a function. Because each element in A must be assigned, but 2 is not assigned. 2 has not been assigned. Now let's look at G. We want to see whether G is a function. What's the definition of G? We are told that G is defined by this. That y is x squared plus x. So y here is the image, and this is the object. The same way, this will be the same way as somebody will have written this. That g of x is x squared plus x. So these two mean the same thing. If somebody writes it this way or writes it this way, it means the same thing. Now, so let's see. Let's look at how the elements will be assigned. We have the objects in X and we have the images. We want to see whether each of these should assign an element in Y. So G of X, by definition, we've said that is x squared plus x. What about G of -1? The object in X there is -1. So this will be -1 squared plus -1. But -1 squared is just 1. Then subtract this and you get a 0. So that means that -1 will be assigned to 0. So I want to write this one in another way. So this way. Okay? So what about the other object 0? So this will be 0 square plus x. X is 0 here. So this will give us 0. So that means that 0 would be assigned 0 in Y. So let's just check if, first of all, this image is there. The image is 0 here. Yeah, it's in Y. It's in Y, it's in 0. Y has 0, so it's 2. -1 will be assigned to 0, and 0 will be assigned to 0 in Y. Let's come to this other object 1. G of 1. The definition says it will be 1 square plus 1, which is 2. That means 1 is supposed to be assigned to 2. Is 2 in Y? Yes, 2 is in Y. The last object is 2. G of 2. By definition, it will be 2 square, which is 4, plus 2, which is 6. That means 2 should be assigned to 6. Is 6 there? Yes, 6 there. Now, so what am I saying here? I'm saying that every element in X has been assigned as a single element in Y. Like -1 has been assigned to 0, 0 has been assigned to 0, 1 has been assigned to 2, and 2 has been assigned to 6. So by arrow diagram, we can have -1 assigned to 0 here, 0 assigned to 0, -1 assigned to 2, and 2 assigned to 6. So that means that G is a function. So G is a function. Now, somebody might ask, what about where a single object has, no, a single image has two objects? Like for instance, this time, this object had this image 0, and this object had the image 0. So two objects having the same image. That one, there's no problem there because the definition only talks about the object. So the definition only says that every object must have a single image. And so what we are saying here is that this object has a single image. And this object has a single image. So there's no problem there. It remains the function. So it's a function. The only thing we refuse is where the object, one object has two images. Where one object has two images, that one is not accepted. It's not a function. But this other case, where one image has two objects, there's no problem there. It remains the function. So you may want to refer to the definition, because the definition says that each object must have a single image. Each object must have a single image. That is what the definition talks about. So just check, does this object have one image? What about this one? Does it have one image? You can even have a case. You can have a case like this, where we have this set and this other one. So let me say this is A, B, C, and this is C, F, G. You can have a case where A is assigned to F, B is assigned to F, and C is assigned to F. This is still a function because you can say one image B has one image, F. C has one image, F. And that's what the definition insists, that every object must have one. But look at this other case. Look at this other case. ABC. E, F, G. Look at this other case. A has that image, B has that image, and C has no image. So this is not a function G here, because it has an image here. I'm just trying to make understand that definition. Look at this other case. ABC, E, F, G. A is assigned to that, and is also assigned to F. B is assigned to this, and C is assigned to this. So this is not, this H here is not a function. And it's that two images. A has been assigned to two elements. Suppose this was set A and this was set B. Let me explain that, or let me stop. We are mapping from B to A. So that therefore means that H, which assigns elements of B to those of A, is not a function, because element A has two images. And so I think that makes that definition clear, that you now know what a function is and what a rule that is not a function. So let me look at the explanation. I have written the explanation here. Let's just go through them, or I've already explained. You can have this. And this is which assigns elements of X to those of Y, if X has not been assigned to an element in Y. I already explained that. B shows that G, which assigns elements, since each object in X has a zero or has one image. I've said that we can also describe as HY. There is only one value in it. For instance, you see me writing that F is going off. Now, here, this is what I wrote. This was another object, and this was another image. We had done it before. I'd say negative what I'm writing there. So I'm writing that F is a set that has elements, but here we have -1 object, and the image is 0. If we did this, and object 0, the image was 1. And that this other one is 1, 2. So this is what I'm writing here. So let's just what I was writing here. I was explaining that at this point. This image is not here because 2 was did not have an action. So we can write this as this, and it was a function. Now let's look at these questions. And I just want to remind you what you've been doing. To determine if this is a function, you just want to see whether, if you plug in any value of X, whether you would have a single image. If plugging in a single value of X, plugging in a single value of X, or every value of X, or every X value, plugging in every X value will give a single image. For instance, This one. If I was to plug in x1, x equals to 1, I would have that y would be, if x is 1, then I would have y to be 2. Y to be 2. So you can see that the object 1 has given me image 2. If I was to plug in 3, for instance, this would be 15 minus 3, and that would be 12. That means I plug in 3. So object 3 would give an image 12. If I was to plug in 0, what will be the image? Negative 3. So you can see that every value of x has only one value of y. Every value of x has only one value of y. And therefore, this one becomes a function. It becomes a function. That's what I've said here. I've said that part here is a function because each input x will give a single output. Give a single output. So that means this one becomes a function. Let's look at this one and see. Suppose I was to put the input x 0. I was to put x to be 0. Then I would have that y squared would be 6. So what about y? Y would be plus or minus the square root of 6. That means the inputs that I put, the input of x that I put, which was 0, has two images. One of the images is positive put 6, and the other is negative put 6. So this single object has two images. What about if I were to put 1? My object was to be 1. So the half y squared is 2 plus 6. So if I put 1 where there is x, so y squared would be 8. What about y? Would be plus or minus with 8. So that means a single input that I put there, which was 1, has given two images, and one is positive root 8, and the other one is negative root 8. What about if my input is 5? If my input is 5, I would have y squared is equals to 5 here to be 10 plus out is 16. So y will be plus or minus 4. The square root of 16 plus or minus 4. So that means that single input of 5 has given me two images. One is positive 4 and the other one is negative 4. So a single input has two outputs. That one disqualifies this one from being a function. Because we say that for each the function, each input should give one output. And that's what I've written here. I've said that for part B here is not a function saying some inputs will yield two outputs. So this is what this is. So if I input a value of x, I expect to get a single value of y. Because for instance, if I were to put here 1, since there's no square this side, or cube, there's no cube or square this side, I expect to get a single value of y. And that's what I've written here to say that. But C is a function with a single output, 13 over 2x plus 10. Now let's look at this other example. I've already shown you how to do this, but f of x is 2x squared minus 3x. Find right negative 2. And that's what I've written here. That's what I've written. Because we are given f of x as 2x squared minus 3x plus 7. But we want f of negative 2. That means when there is x, just write negative 2. And this will be 2. Negative 2 squared minus 3, negative 2 plus 7. And so what this one, this is 4 here times what? 8. Negative times negative, the positive. 3 times 2 is 6, then plus 7. This gives you 21. And so that's what I did and got this. So we're just substituting where there is x, we substitute the value. Even for this one, where there is x, substitute 3. It's very easy, you can do that. And where there is x for part 3 here, or part 3, substitute a, and substitute this where there is x, substitute this where there is x, substitute this where there is x, and you have those answers. So let me just show you what I did, because for the sake of time, just show what I did. So for part 1 is there, part 2 is this, x I put 3, so you get 16 as the answer. For part 3 is the same thing, where there is x I put 2 and 3, but where there is x, put a. This was the question. So where there is x, just put a, and when you put a, what you will get will be f of a. And that f of a will give you 2a squared minus 3a plus 7. So if you put a where there is x. What about for this? Put a where there is x. That's number 4, where there is x, put a. So that will be 2, just a minute, that will be f of a plus 1. So that is 2, where there is x, put a plus 1. Minus 3, there is an x here, put a plus 1. Then plus 7, this one has no x. We know how to expand it. We know how to expand it. We know that a plus 1 square is the same as a plus 1 multiplied by a plus 1. This one everyone knows. And then we know that we shall multiply this to get a square, and then multiply this to get a, then multiply this to get a, then multiply this to get 1. And so this will give me a square plus 2a plus 1. So that's what I have here. 2 into a square plus 2a plus 1. Then minus 3a minus 3. I just expanding this to negative 3a, negative 3, then plus 7. You can also expand this now to get 2x squared plus 4a plus 2 minus 3a minus 3 plus 7, and collect like terms. And collect like terms. That's what you can do. So when I did this, what I got, because this one move slowly and see what I get with them. Even number 5 is here. Go through it and sell. Go through it at your own time and see whether you get what I got. That's number 6. You can have those answers. I wanted to make this number 6 here so that at the bottom it was not very good. It is now very good. So that is the working. So you can at your own time go and see whether you get it. Then after that you have this exercise. Attempt this exercise, and question 1 is here. What does question 1 say? X are sets consisting of 1, 2, 3, 4, 5, and 6. Let f g those of y defined by arrow diagram functions give results. So function f is here, function g is here. So you tell whether f here is a rule, whether g is a rule by looking at how the elements of x have been assigned those of y, and the same time those of y, and then tell whether f is a function and whether g is a function. Once you are done with that, you can come to this other one. You have h here and whether r is a function by just looking at how it has been assigning elements of x to those of y. There's this other question here. It's let f assigning elements of x and y and g assigning elements of y based. We've looked at a similar position. So the question is, are g and f functions give results? Just go through our examples and see whether you are able to answer this. And then there's this one, I think the last question. If gx is x plus 3 out of x minus 2, find this distance. Now, so earlier on, I indicated that I'll be looking at the domain and the range of a function later. So it's that time that I want us to look at domain and the range of function. So I begin by the definition. And I already said this, that if we have a function assigning elements of x to those of y, then x here will be called a domain. X is the domain. And y here is the codomain. I had already indicated this. Y is the codomain. And now look at this scenario. I have x here. And I have this y. I have this ABC. I have E, F, G. A is assigned to E, B is assigned to E, and C is assigned to F. Yeah, this H is a function. This H is a function because I can see that every element in X has an image and a single image. So H is a function. But that is how I want to say, because we've already looked at that before. What I want to introduce is the word range. So you notice that in the codomain Y, we've only assigned to E and F. G has not been assigned to. So therefore, the range of this function are the elements in the codomain to which we've assigned. So it's a set of those elements. A set of the elements in the codomain to which we have assigned. So for instance, in this case, in this codomain Y, we want to assign it to E and F, and therefore the set of E and F makes the range. G is not in the range, but it's in the codomain. And so all those explanations is what I've put here. What I've put here, I've said that if F is assigning elements of X those of Y, if it's a function, then X is the domain of F, while Y is the codomain. Then the range is defined here. The set of all the elements in Y to which elements of X have been assigned is called the range of X. And I've also stated something. I've said that thus the domain corresponds with the set of X values, while the range corresponds with the set of Y values. When if this is a function, then what I'm saying is that what's the domain? The domain is the set comprising of 0, these objects 7 and 3. This is the domain. What about the range? The range are the images. The first image is -1. You have this other image which is -6. You have this other image which is 4. Let's just go back. I've said thus the domain corresponds to the set of X values, which is the caliber, and lists the elements inside the caliber. While the range corresponds to the set of Y values. So the range is the set of Y values. So the set had a bracket in a list the Y value, which are -1, -6, 4. So that is the range. So it's good for you to get what explanations there. Very important explanations. Now, look at this other point, that if only the root Y is equals to X, then X is given. If only you're given a rule, for instance, you're given Y equals to X squared plus X. If only this is given, and you're not given the values in X, the set X, you're not given set Y. If only this is given, then this is very important. You see, then the domain, sometimes referred to as the natural domain of the function, will be, let me just delete this, and then it's called down. That is the whole thing. Okay, so if only this function is given, then the domain will mean all the x's that can be plugged into the equation and have the function exist to obtain real values. So that means if, for instance, you're given this function, y equals to x squared plus x, then what is the domain? So the domain is now think of what x values can I plug here, and the equation will still have a real number, a real number. What x values can I plug here? And you notice that any value that you plug here, it has to plug in. Then I get y is the real number. If I plug 3, y is the real number. That means if I was to plug all the real numbers, plug in 3, plug in 4, plug in -5, plug in -1,000, plug in 1 million, we still have a real number. So that means the domain will be all the real numbers. The domain will be all the real numbers. Or if you want, you can say the domain will be all the numbers from negative infinity to positive infinity. All the numbers from negative infinity to positive infinity. And I'm using these brackets to mean that negative infinity is not included and positive infinity is also not included. But all the numbers in between will form the range. No, not the range. Will form the domain. All the x values that can plug, let me just go back there. all the x's that are plugged into the function and have the function exist to obtain a real number for y, they form the domain. What about the range? The range of the function, if we have only given this, then the range of the function will mean the set of all possible y values, all possible y values that a function can have when elements of the domain are plugged into the function. For instance, if I'm given y is x squared plus x. If I was to plug in 0, if my domain has a 0, then y will be 0. Well, if I plug in 2, y will be 4 here plus 2. If I plug in 1, y will be 2, and so on. So all those possible values that can be obtained when the values of the domain are plugged into would then form the range. That is, if only the equation is given. So let's proceed to some examples. There's a very important point here. Very important point here for your notes. This implies that to obtain the domain, we need to avoid division by 0, logarithms of 0, logarithms of negative numbers, and square roots of negative numbers. So we'll be looking at examples to make this point clear. Now let's see the domain and the range. Just before we do that, let's remember that the domain will be the x value. The range will be the y values. Just a minute. So we will say that the domain will mean the x values and the range will mean the y values. So if you're given a graph like this and you're asked about the domain, just give us the x values, and for the range, you give us the y values. So let's just hold this one down. So you just take where does the x values begin and where do the x values end for you to tell us the domain. When I look at this graph very well, I'm seeing the x values are beginning from -2 to +2, not yes, from -2 to +2. And I'm also seeing the -2 is included because these are continuous graphs. It's not dotted. If it would be dotted, then we would say that the values on the boundary are not included. But these are continuous graphs, and therefore, the domain are the values -2 to +2, and they're both included, and because of that, I use this bracket. I use the square bracket because they're included. If they will not be included, then I would use this other bracket. I would use this. But since -2 is included, and I can see it, that is a continuous graph, and this is also a continuous graph, I use the square bracket. And I think that point is very clear. So this is the domain, the set of the x values, So we have -1, -2, all these x values here. -1 is 0, is 0 here, 1, 2. All these values are in the domain. What about the range? The range are the y values. So let's see, where do the y values begin and where do they end? So the lowest y value here, the lowest y value is -3, is included, and the highest y value that I see here is +7. That means that the range of this function is -3, +3, and the 3 positive is included, and the negative is also included. So this is the range. So we need to look at another example. But just before that, what was my explanation? My explanation here was that recall that the domain are x values, so that from this figure, these values extend from -2 to +2 inclusive. And therefore, the domain will be this. And remember the square bracket, I've explained why I'm using them. And the range of y values, they extend from -3 to +3 inclusive, meaning therefore that the range is this. If I'm given a graph, I can tell what the domain is and what the range is. What is the next example here? Use this graph to determine the domain and the range. So I just want to see the domain. I want to see where do the x values begin and where do they end. I'm not seeing where the x values begin. What I'm seeing is that this is the left side. So the x values, you cannot say they are beginning at -2 because this graph is still continuing. You can see the arrow here, meaning that it's still extending to the left. The graph is still extending to the left. And this other side, you can never say that this point, you can never say this point is the last x. Now, the graph is also still extending to the right. It's still extending to the right. So what is the domain there? The domain will be all the real numbers. You can write it that way. This is the domain. Now, if you do not want to write it this way, then you would say that the domain is between -infinity to +infinity. But then -infinity is not included, and +infinity is also not included. So you can write the domain like this or like this. And we've already said that this is so because this graph is still moving to the left. It's still moving to the left. You can see the arrow there is not the last point. Not the last point. This is not the last point to the right. Still going up. Still going up. You can see it began from it, crossed 2, it crossed 4, it has come up to 5 here, and it's still going, it will go even up to 10 and so on. So you can tell all the real numbers, or you can just say that the domain the value between -infinity and +infinity. But -infinity and +infinity are not included, and therefore put those brackets. What about the range? What is the lowest value of 1? So we begin from there. Let's see the lowest value of y. Yes, I can see it here. What is this? 4. What is this? This is 5. I can see this is 5. 5 is down here. So this is 1, 2, 3, 4. So the lowest value here is -4. -4 is the lowest value. What about the highest value of y? The graph is still going up. The graph is still going up. That means that the lowest value is 4. The graph was continuous, so it's -4 is included. And the largest value, the highest value of y is +infinity, which is not included. Which is not included. And so that is the range. I'm just teaching you how to identify the range and the domain. If a graph is given to you, And this is the explanation here. For the sake of your notes, because you are writing notes, you can have this. There's this other graph here. We have to determine the domain and the range. Let me just look at the domain first. I want the x values. Yeah, I can see that this ends here. This is where it ends. And here it's still going because of the arrow, it's still going. So what is the lowest x value? What is the lowest x value? It is -1. Is -1 included? This point here is a circle. It's open, not included. -1 is not included. If I use that, I cannot use square bracket. Now, what is the highest value of x? It must go to the positive one, but I can see that the graph is still extending to the positive. Still extending to the positive. It has not reached its end. So that means the highest value is infinity, which is also not included. You can never include infinity or negative infinity. So this is the domain. What about the range? The lowest value of x, no, the lowest value of y. These are the values of y. The lowest is -1, which is not included. What about the highest? This graph is still going up. Still going up. So the highest will be infinite, which is also not included. So this becomes the range and this is the domain. So just look at my explanations and then we proceed to the next example. My explanations are here that the domain is -1 infinity, not included in any of them, and the range is also that, and we don't include any of them. And because we use that open circle there, it means that that graph does not exist at that point, does not exist at this point, and therefore this point is not included. Let's look at the other example. We are using the graph to determine the domain. I want to begin the domain. I want the lowest value of x. The lowest value of x must be to the left, the lowest value of x. And I can see the graph is that means the domain, the lowest value there, you look at the domain, the lowest value is -infinity, not included. What about the highest value of x? This is the end of this graph, the right. This is the end. That means the highest value of x is 2. This is the shaded. This is the shaded. It means this point is included. So I use this bracket. It means that point is included. So this is the domain. What about the range? The y values. The lowest y value is here. Because these are the y values. So the lowest is -1, which is included. What about the highest? This graph is still going up. It's still going up. It's still going up. You can see it's still going up. That means the highest y value is infinite there, which is not included. So this becomes the range. So just one explanation and then we proceed. This is the explanation. This is the explanation here. You can have it for your notes. Now I want you to try this, and before I give my explanation, I want you to try this. Where's the graph? It's here. I want you to tell me what the domain is and what the range is. Domain, range. So we have a few minutes to do that. Okay, we can now just look at what we have as explanations. The domain, we are looking at the x values. I can see that the lowest x value is not known. The graph is still going to the left. The highest x value is also not known because the graph is still going to the right. That means the domain is the whole real number, or if you want, negative infinity, positive infinity, not infinite. That is the domain. That's the domain. You can say the whole real number, or you can say this. What about the range? About the range. What is the lowest y value and what is the highest y value? I can only see one y value, which is 4. I can only see it's negative 4. I can only see negative 4 here as the only y value, and therefore the range will be this set comprising of negative 4. That will be the range. So let's look at the explanation. That's what I've explained here. I've said that the domain will be this, and the only y value is negative 4, and therefore the range. Want to look at this example? The example says, let G assigning elements of x those of y be a function defined by the following diagram. Determine the range of G. This is very easy. You want to determine the range. Of course, it's a function. So I just want to look at what values of the domain, what elements of the domain have been mapped to. The elements of the domain that have been mapped to are x, y, m, and p. These are the only elements of the codomain. Yeah, elements of the codomain that have been mapped to are x, y, m, and p. So this is the range. This is the range. So if you're given a diagram to tell the range, it's the range. And so those are my answers. And look at this other example. Let P be a function defined on two sets N and P, such that P assigns to its parent, where set A is this and set B is this. And the range of P is very easy. This person is just asking you, where will 1 be assigned? What will be assigned to 1? Where will 4 be mapped to? Where will 9 be assigned to? Where will 9 be assigned to? And I'm seeing the definition here. Is that it's not a person the object. That the object has its square root as the image. So in other words, if I'm asked about the range of P would be the set, and it must be a set of what is the square root of 1? I'm using this definition. What is the square root of 4? What is the square root of 9? What is the square root of 49? What is the square root of 25? This is the range. That's how you do it. Just use the definition. Right? Use the definition of the mapping of that function. Look at this other example here. Determine the domain and the range. And we did this earlier. And we said that the domain are the x values. The set of the x values. The set of the x values is the domain. The set of the x values. And you can see that is what I have here. What I've just ticked there. What I have here. The set. And it must be in those brackets because it's a set. What about the range? The range will be the set of the y values. The set of the y values. The set of the y values will give us the range. In any order, you don't need to worry about that, but you can see rearrange like you can be negative 7, basically, but you can see a rearrange that. So you need to put in any order. It's a set and vice versa. Now, the next thing what is even and odd functions. We need to know when do we say that our function is even and when do we say that our function is odd. By definition, a function assigning elements of x to those of y would be said to be even if f of negative x is the same as f of x for each x in x. And it will then be said to be odd. Another function f that assigns elements of x to those of y would be said to be odd if f of negative x is the same as negative multiplied by f of x for each x. So, I just want to put a few examples and see whether those functions are odd or not. But what is very important is this definition. That if f of negative x is the same as f of x, then the function is even. But if f of negative x is the same as f of x multiplied by negative, then the function will be odd. If none of this is true, then the function is neither even nor odd. Neither even nor odd. If none of this is true. Now, the question is verify analytically whether the following functions are even, odd, or neither. So just go through the definitions. We've been given f of x. So let's just find f of negative x and store it. F of x is here. What is f of negative x? So while there is x, just put negative x. This will be 3 negative x squared minus 2 negative x squared. Oh, this was negative x raised to 6. Then minus 5. So what does this give us? Negative x raised to 6 will be x raised to 3 x raised to 6. And this will be negative 2 x raised to 2. Then negative 5. So what I'm saying is that f of negative x is of course the same as f of x. You can see that the same. And so that means therefore that this function here is even. This function is by definition. By definition. You can see that it's even. If f of negative x is the same as f of x, then it's even. That's what I've done here. That's what I've done here. I've said that we simply replace x with negative x and compare the result to that of f of x. So when I do that, f of x is here, f of negative x is this, And you can see that this is the same f of x. And so what is my conclusion? That f of x is even. F of x. I want to try one more example, then you look at the other examples. Just look at my work and try viewers. I want to see f of t, no, t of x is given to us as plus 2x plus 4. So the question is this function even or odd? So let me see. What is f of negative x? So f of negative x would be negative x raised to 7 plus 2 negative x raised to 3 plus 4. What will this give us? Negative raised to an odd number is negative. X raised to 7 will be 7. X raised to 7. Negative raised to an odd number will be negative. X raised to 3 plus 4 is plus 4. Now, even if you are to try to factorize this, put a negative outside. Just before that, the result that I've just obtained is not the same as g of x. Is not the same as g of x. Because g of x was positive everywhere. So it means that g of x is not even. Because g of x is not the same as g of negative x. And therefore g of x is not even. So if it's not even, then we proceed to find out whether it's odd. So to find out whether it's odd, I need to get negative and multiply g of x. So negative times this g of x will be negative x raised to 7, negative 2x cubed, and negative 4. And I'm also seeing that this is not the same. This is not equal to g of negative x. Not the same. It's not the same. Negative multiplied by g of x is not the same as g multiplied by negative. No, yes, g of negative x. So then it means that g of x is not odd. It's not odd. So it was not even, it's not odd. It's therefore neither odd nor even. Therefore, neither odd nor even. Let me just look at my explanation for number 2. Because it is the one I've been doing. Number 2. I began with this, then I found g of negative x to be this. Then this one is just supposed to be g of x, not f of x. Supposed to be g of x. So g of x is not given. So we then determine if it's odd. So we multiply. And so therefore, g of x is neither even nor odd. Neither even nor odd. Just look at another example. Then I leave you to do the rest. It was h of x. H of x is this. So I just want to see whether it's even or odd. I first of all get h of negative x. So that means it will be x, negative x raised to 5 minus 4, negative x raised to 3. What I know is that negative raised to an odd number will be negative. And that negative raised to an odd number will be negative. So that negative times this will be positive. So this is negative, no, h of negative x. And I can see that it is not equal to h of x. So h of x is not even. If it's not even, let me confirm, let me check whether it's odd. So I get negative multiplied by h of x. So if I multiply this, I have h of x. So if I multiply it by negative, I will have negative x raised to 5 plus 4x. But I can see and this is equal. So what that means that h of negative is equal to negative multiplied by h, and therefore h of x is odd. H of x is odd. Now, using this example, you can do the rest and just compare your result with the one. This is I'm just showing my this is my working for number 4. And this is my working for number 5. So you do yours and compare with mine. Then after that, you have this exercise to do. Are the following functions odd, even, or neither? Verify analytically. So you try this one. I want to teach you about inverse functions. So what we know about the inverse function is that, for instance, if x was assigned, if f was assigning element of x to those of y, then the inverse of f will be that function which will be assigning elements of y back to those of x. So we shall denote it as f inverse. We shall denote it as f inverse. So this is just a function that they're assigning elements of x back to those elements of y back to those of x. And after I've written, I've said that for any function of y, there is an inverse which assigns elements of y back to x. Now, the other important point that I've said that we should not confuse the inverse of function with this. With this. They are not the same. 1 over f is not the same as the inverse of function. They are not the same. So that is a point that I've noted here. When you read this, it's not so. When you read this, not so. Find this point here. Now, so before we go into determining if a function is determining the inverse of function, we need to know that a function would have an inverse if it's a one-to-one function. So I need first of all to teach you what is a one-to-one function before I go into determining the inverse of a function. So that's how I've written here. I've written that point here, and I've said that it's important to know that not all functions have inverses. And therefore, before trying to find the inverse of a function, it's necessary to determine whether or not it has an inverse. And I've said that only one-to-one functions, which we also call injective functions, have inverses. Only one-to-one functions have inverses. So I want to teach you what is a one-to-one function. Let us now look at one-to-one functions. And I'll begin by these diagrams. I'll begin by this diagram. I'll begin with this set x. And set x has elements a, b, c. And I also have set y. Set y has elements 1, 2, 3. I want this to be assigned 1, this be assigned 2, and this be assigned 3. What I'm seeing here is that One object has one image, one image has one image, another one has one image. And if then the images are also different. If the objects are different, then the images are different. So this is a one-to-one function, a one-to-one function, which we also call injective function. Injective function. Let's look at this. We see that x 1, 2, 3, set y have this. This object has one image. This object has one image. This object has one image. This is not a one-to-one function. Because I have two different objects that have the same image. Different objects, same image. This is not a one-to-one function. It does not just necessarily mean that one object, one image. No, it does not just necessarily. It also means that if they are different, if the objects are different, the images must be different for it to be a one-to-one function. So the definition is here. Let F, assigning elements of X to elements of Y be a function. Then F is set for one-to-one or injective if every distinct, the word distinct here means different. If every different object in X is assigned a distinct, different image in one. That's a very important definition, very important. And I've already used those diagrams to make it clear. So you can at your own time look at those diagrams. So mathematically, a one-to-one function, if a function is a one-to-one, what it means that if you have two objects in X which are different, that means where X is not equal to Y, then we expect to see the different images. Then the image of X is f of X can never be equal to the image of Y. These images must be different. And that's what I've written here. I've said that a function f is one-to-one if whenever we have two objects, X and Y, which are different, we are guaranteed that their images will also be different, or their outputs will also be different. Very good. So what I want to look at are examples of injective functions or one-to-one functions. Let f that assigns the real numbers to the real numbers be a function where f of x equals to negative x squared. That means the image of x is negative x. Or when x is the input, the output repeats. Then the question is this one a function, a one-to-one function? Is it a one-to-one function? So what would be the function? Two different inputs. Would I get two different outputs? And I tried 35 and was 5 to my inputs. F of negative 5 will be negative. I'm using this definition, will be negative 5 squared. And this is negative 25. F of 5, using this definition of the negative 5 squared. And this is negative 25. What I notice here is that I had two different inputs that have given me the same output. 5 was different from -5, but I found that the input would be -25, which is the same as -25. Since these are two different inputs, and they have given us the same output, it means that this function here is not one-to-one, is not injective. So I've said clearly, F is not one-to-one, since if I'm given two inputs here, which are different, their output will be the same. Their output will be the same. So that makes it not one-to-one. On the other hand, now, just before that, I used -5, a real number. You see, we're told a real number. So just use any real number. It's not necessarily -5. You can even use 2 is a real number. 3, all the numbers, no other complex numbers, they are real numbers. Suppose you can even use -2 and 2. These are real numbers. Input them here. They are different. You can see they're different. But now, what about the input? F of -2, the -4. And this is the same as F of 2. F of 2 will also be -4. So, different outputs have given, no, different inputs have given us the same output. And that means the function is not injective. What about this function? G of x, which is x. Is it a one-to-one function, or is it not? Let me pick a real number 2. Let me pick a real number 2. Another real number -2. Clearly, 2 and -2 are not equal, they're different. Let me see their output. G of -2. Using this definition, it would be -2. G of 2, using this definition, would be 2. So the outputs also different. The inputs are different. The outputs are also different. So this function is one-to-one. This function is one-to-one. Now, determine if these functions are one-to-one. These are very easy. Let's see. This input has this output. 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 Now, we will not have one output repeated for two different inputs. Every input has its unique output. So this is a one-to-one function. This is a one-to-one function. What about this one? This one, I can see this output here. The same as this output. And the inputs were different. This input was 8, and this one was 7. So two different inputs have given us the same output. This is not one-to-one, not a one-to-one function. It's not a one-to-one. Okay, some books write it this one-to-one function. Others write it one-to-one function. Others write it one-to-one function. So there's no problem. It depends on the book you are reading, and the information is the same. And I've also said that it's so-called injective function. So The explanation is that onto functions. Let me just explain. Let me give you this x set 1 a b c 1 2 3. This is not there. This is not here. This is not here. Every element in the core domain is a member of the range. The member of the range. Here you can see that all elements who are in the core domain have been mapped to, have been assigned an element here in X. So this is an onto function. This G is an onto function because all these elements have been assigned elements. This was X, Y, A, B, C. 1, 2, 3. This has been assigned to that. This has been assigned to that. And this has been assigned to this. 3 has not been assigned. This is not an onto function. Not is not an onto function. This one is onto. So by definition, let's so if it's the range, look at the range. The range is your whole piece, and it's going to the range is just 1, 2. It's not the entire core domain, not the entire core domain. Therefore, this is not. So it's very good that we now understand what an onto function is. An onto function is also known as a projective function or surjective. Just one example. Example here. Let X be a set comprising of this and Y be a set comprising of this. Let G, assigning elements of X, those of Y, be defined by this. And the question is this G onto? We just have a domain, and this is the domain. We want to see whether the whole of this will be assigned to, whether all these elements would be assigned to. And this is the definition. Where is -2 assigned to? Using this definition, -2 would be assigned to, when I square it, I get 4. Assigned to 4. So 4 has been assigned to. Where will -1 be assigned to? When you square it, get 1. So -1 is assigned to 1. I'm squaring it because of this definition, and you already understand. You can take this from the start. Where is 0 assigned to? So 0 square will be 0. Where is 1 assigned to? 1 is assigned to 1 square, which is 1. Where is 3 assigned to? 3 is assigned to 9. So all those elements of the core domain have been assigned to. And therefore, this function G is onto. I will then explain using a diagram, and my diagram is here, and we watch my diagram. I will explain using my diagram. This is how it is. Now, let's look at this, whether it's onto. This is X, and this is Y, and F is defined by this two. The modular. So where is -3 assigned to? -3 is assigned to the modulus of -3 plus -3 here, here, then minus 1. So this modulus, it means it comes out a positive. So there should be 6 here. Positive 6 minus 3, which would be 3, minus 2, which is minus 1, which would be 2. So this would be assigned to 2. So 3 would be assigned to 2. Would be assigned to 2. What about negative 2? So just change where there was 3, negative 3 to negative 2. Negative 2, negative 2. So this would be positive 4 minus 2, that comes to 2. Then minus 1, that comes to 1. So negative 2 assigned to 1. You can go through properly. This was negative 3. Go through properly. If supposing you miss something, you can, at your own time, slowly you can rectify that. Now, what is the next element? Is 1. What will be 1 assigned to? So it will be 2 modulus of 1 plus 1 minus 1. And this is 2. This is 2. So 1 is assigned to 2. So we've assigned it 2. We've assigned it to 1. So let me see. We are already here. And then we come to this. Where will 2 be assigned to? So where there is x, just write 2. Where there is x, just write 2. And here it's 1 plus 4, that would be 5. So we are assigned to 5. So 2 is assigned to 5. Then finally, negative 4 here. So it will be 2 into negative 4, then negative 4, then negative 1. This is negative 5 here. And this is positive 8. That gives us 3. So 4 is assigned to 3. Negative 4 is assigned to 3. So 3 has been assigned to 3. So you notice that the range comprises of 1, 2, 3, and 5. So the range would be 1, 2, 3, and 5. 4, 6, and 7. So the range is not the entire quantum range. And therefore, that means that this function f is not onto. And that's what I was saying. My answer here, that the range is 1, 2, the set comprises of 1, 2, 3, 5. This is not the entire y or the entire quadrant. Hence, f is not onto. I've used a figure here to show you the expression. You now to put this information in these arrow diagrams. In doing it from the start, this is my arrow diagram. You can look at it later. Now we go back to the inverse of a function. Remember we one-to-one or injective. So we then began by looking at what an injective function is. We are now ready to go back and determine the inverse of it. If f of x is a function, then the following steps will be used to get the inverse of f of x. The first step is to determine if the inverse of f of x exists. That is, determining if the function is one-to-one. And if it's one-to-one, then you proceed as follows. You go to step 2, and step 2 says that replace f of x by a y. Then go to step 3, which says that where there is a y, write an x, and where there is an x, write a y. Replace every y with an x and every x with a y. That is step 3. Then you proceed to step 4. That you solve the equation in step 3 for y. You make y the subject of the formula in step. The y in step 3, make it the subject of the formula. Then you come to step 5. Where there is a y, just write f inverse of x. And you would have found the inverse of x. So these are the steps. Let me just show you how to follow these steps in an example. Find the inverse of the following functions. The first function is this. First of all, we determine if it's one-to-one. If it's one-to-one, that is, if you have two objects which are different, will the images be different? If you have two different inputs, will the outputs be different? Here, these are one-to-one. So let's just proceed and find the inverse. Step 2 says that where there is f of x, write 1. Where there is f of x, write 1. And then step 3 says that replace y with an x. In other words, where there is y, write x, and where there is x, write y. That was step 3. And then step 4 says that make this y the subject of the formula. That means leave y on one side. So for example, if I left it here, then I would have x minus 1. I would have x minus 1. And dividing both sides by 7, I would have that y is x minus 9 divided by 7. This was step 4. And then what step 5 said is that where there is x, where there is y, write f inverse of x minus 9 out of 7. So this is the inverse of that function. So if it was not the element of x, it was of y. This is the function of not the element of y. If you want to x over 7 and sine of 7. And that's what I did. I have my work in here. Just repeating what I was doing, but the work is what. Let me do this. So it's good for you to first of all determine if it's one-to-one. This function here is not one-to-one. Because if I was to put an object, let me say 2 and negative 2. Two is not equal to negative 2. What is the image? What is the image? So, f of 2. What will f of 2 be? It will be 3 2 square minus 7. And this is 4 times 3. And this is one-to-one, and therefore it has no inverse. It's not one-to-one, and therefore it has no inverse. And the best thing of what I did, I said that f of t, since it's not one-to-one, it cannot be horizontal matrices. because this is another way to test if a function is one-to-one, but I've not taught you this in this course, in this lesson. So it knows. Let's look at part 3. So it's one-to-one. Now, this one, different outputs. That means this thing is a one-to-one without our so the procedure is the word where there's Q of x by 1. And the other step is where there is y right x and where there is x by 1. Where there is y right x, where there is x by 1. And then you make y the surface of the formula. This one is under the square root. So that means you square both sides. When you square both sides, this will equal 2y minus n or x squared plus 5 is 2y, or y is x squared plus 5 out of 2. So where there is y, write the inverse of this. So therefore, g inverse of x is x squared plus 5 out of 2. Now remember this is x squared. Just how we find the inverse of a function. And using the same example and substituting, you can compare your result with. Most importantly, before you find the inverse, check whether the function is one-to-one. And if it's one-to-one, then it has an inverse. If it's not one-to-one, it has no inverse. So you will do that and compare your results with mine. Let me just show you my workings for the rest of the questions. So question is C. My working is here. So question is C. I've done it with you. Then question D. Working is here. Doesn't follow. Do yours, and then compare with mine. Do yours first. And then we have this other question. E with this one. You can always pause the video and write, compare. After you've done it, pause the video and then compare the results. If you find your wrong answer, then you pause the video and look at my work. Now find the inverse of this. Find the inverse of this. To find the inverse of this is just the change. Just the change what was the y value to become the x value, and what was the x value to become the y value. So that's what I'm written here. The inverse of this kind of function is found by the change the entries in each ordered pair, and so in the given pattern. So this is negative 3, this is 23 negative 3, this is 15 7, and this is 19 8, and this is 39. So that is the inverse. What about the domain of the inverse? The domain, this is the inverse. So the domain would be the values, the x values, and the range would be the y values. The range would be the y values. So the domain is the x value here, and the range are the y values. So you have to look at that. So somebody might ask you to find the inverse, and find the domain of the inverse and the range of the inverse. show you how to do that. You can attempt these questions. Are the following inverses the following functions 1 to 1? Okay, those are the questions. There's another question here. Find the inverse of the following functions. Let me just show you that one again. Find the inverse of the following functions. And these are the functions. Find the inverses. So first of all, as we say, determine if it's 1 to 1 before you find the inverse. Now, lastly, we want to look at composition functions. So that is where I will end my today's lesson. I begin by defining, and I'm saying that if f and g are two functions, such that f assigning elements of x to those of y and g assigning x to y, then a composite function is element of I have elements of x here and I have elements of y. So I have f assigning elements of x to those of y. Then it stops here. Then g takes over and assigns those of y to those of z. So these are functions. One has assigned element x to those of y, and another is to assign the y one to those of z. Finally, suppose the f assign the n to 1 and g assign 1 to w. These are two functions. We now want one function that can assign a straight to w. One function that can assign a straight to w. Or one function that can assign a to those of them. And that is what we shall call a composite function. How do we denote it? This is denoted by G composition. So the last one here comes G composition. Okay. So this is a composite. One function. The count G composition. So that means we place f of x inside g of x. So the composition of two functions f and g is the new function we get by performing g first. And I'm going to show you that the last one comes first. And then performing f is denoted as this. Or as this. So you can have this. This is what I have written this way. We substitute f of x inside g of x. Now because you are writing notes to have that, let's look at an example. Let x be this set, y be this set, and z be this set. Let x assigning elements of x and y be defined by this, and g assigning elements of y because of that is defined by this. And g position. By definition, I've already said that G composition F can be written as G f of x. Remember that this is what we have, this is our G. This is our G of x. This is our G of x. And it equals to x minus. So what this definition means is that while there is x here, instead of x, write f of x. And if you understand it that way, then it becomes great. Instead of x, write f of x. This is our f of x. So there is an x here. So instead of this x, write f of x. 2x. Then minus 2. So this becomes 2x minus 1. This is our composition function or our composite function. So once if you understand this relationship, then it becomes very easy for you to do it. That's what I was done here. Let's plug f of x by g of x. Plug f of x into g of x. Maybe another example will make it clear. But I've done it here. But I've done it here. And even I even use the wisdom that you can now you know how to draw the arrow that comes. You can look at it and see whether what I do here is correct. Of course it's correct, just draw yours and compare. This diagram is not part of the question. The question we've already done is already done the question. I'm just using this diagram as to illustrate so that you understand the question. Now, let me do 2 or 3 here. Let f of x be this and g of x be this. Find g composition f of g. Plug in g of x. Plug in g of x. And that's just done. And you know, this is not the same as this is not the same as G composition F. It's not the same. Because G composition F means in G plug in f of x. If you understand that, it becomes very simple. We are given the equation of f of x, been given as 3x plus 1. Now plug in g of x. So if I plug in g of x, where there is x, write g of x. There is an x here, write g of x. Then there is plus 1. So what do you get? 6x squared minus 15x plus 1. And that is the answer. That is the answer. It's very easy when you are dealing with these things. When you are doing these things, you enjoy it. That's what I got. That's how I got this answer. Now look at this other one. G composition F, whether somebody writes that as this, it means the same as this. It just means the same as this, and it also means the same as this, depending on the book we are using. These three mean the same thing. That where there is G plug in F of x. And what is G? We have been given G as G is 2x squared. So while there is f of x, f of x is x. It was squared. Then minus 5x. Minus 5. But while there is x, right, f of x is 3x. Plus. And you know how to expand this. This will be 2 into 9x squared. Is it plus 6? Then plus 2. Plus 1. Plus 1. Then minus 15x minus 1. And you can simplify this. Let me show what I did. It's the same thing. The same thing. I've done the same thing. Just showing you that this is the same as that. Also the same as this. And then I proceed. Now, so the only thing I want to show you now that I have not shown you is this. Look what. There was an X. But these are two. Look at this. This A, one will have written it this way. One will have written it this way. One will have written it this way. F composition G with an X here. So that means in this result, just substitute X in the two. What did I do? I substitute X in the 2. From above, we have this, that was the answer we got in N. The answer we got in N. So substitute that with that 2. Substitute the answer of A with that 2. Where there is X, put that 2, and you get negative 5. The alternative is what I've shown. I've said that if you're given this D, you're given this D, somebody else would have written it this way. Somebody else would have written it that way. That means, first of all, find the G of 2. You have G of X. You have G of X. What is G of 2? G of 2, where there is X, put 2. This would be 4 times R, which is 8, minus 10, which is negative 2. And so, this therefore is the same F composition negative 2, which is the same as somebody else should write it as this F negative 2. Somebody else can write that. F negative 2. Because G of 2 is negative 2. So this is negative 2. The whole of this. So it's that. So where there is F, put negative 2. Where there is F. So G of negative 2 will now be negative 6 plus 1, which is negative 5. And that's what I did. So we just get my alternative way. Alternative way is this. In alternative method, use that. You can use the numbers. Now, so the rest of the questions, I just show you my answers. You try yours and see what the bill is, because the one thing is very is what. So just show you my workings for the rest of the questions. And again, this other one, which says that given this and this, find G composition H, then find the domain of this. I show you my working, and you can follow that. This is my working for that question. And if you have any question, you can write in the comment section. Then I respond to maybe an explanation. But we already looked at the domain and the range, so you can use that knowledge. And to end, you have this exercise to look at. Try this exercise. And that brings us to the end of today's lesson. If you've not subscribed to my channel, remember to subscribe so that whenever I load the video, you can automatically get it. Thank you.